Welcome back to another lesson with me, Mr. Wong. Today we're going to be looking at precipitation reactions. Before we go on, let's have a look at these three equations that are not balanced and let's try and work our way around to getting them correct. So going through each one at a time, remember when we come across balancing chemical equations, always work across the element that appears only once on both sides and try and balance it out like so. In question 1, we have boron as being, or bromide as being 3 and bromide being 2. Aluminium is balanced as a 1-to-1 ratio, but obviously we need to make sure boron is balanced. Now the best way I like to do it is if we see there's an odd number here, try and make the number even. So let's say I put a 2 here, okay? And then boron is already 2, so I have 2 aluminiums. 2 times 3, I have 6 bromides in total. So to make this into a 6, I need a 3 here. And so that's my equation. You can also try and work out the states it's in. Now, aluminium is a metal, and in normal circumstances, metals are solids at room temperature. Bromide is a gas, or bromine is a gas, and so they make a solid there. Okay, next we have is silver, H2S plus HO2, silver 2 sulfur plus water as well. So to work that one out, we have silver as being 2. Let's just work out silver, 2 there. Sulfur is 1, so that's all good. H, we have 2 H's, 2 H's. We have 1 oxygen, we have 2 oxygens. So let's make this into a 2 to make 2 oxygens, but now we also have 4 hydrogens. So I'll put a 2 also here. Okay, what I notice is I also make the sulfur into 2. So put a 2 here to make it 2 sulfurs each here. And that makes it to 4 silver atoms, and so this changes into 4, and so now it's finally balanced. In my last equation, I have a H2SO4, a potassium hydrocarbonate, and then we have these equations over here. So let's look at what appears only once. We know that potassium only appears once, so let's try and balance potassium first. So 2. And then let's look at what else we have. Now sulfate is just one entity, so we don't have to worry about balancing that. So this over here, we're not touching it anymore. Let's look at what else we have. Carbon is something that appears only once on both sides. So let's try and balance carbon here. So 2 carbons, 1 carbon here. So I'll put a 2 to make it balanced. And then we've got hydrogen and we've got oxygen. Let's look at the hydrogen first. I have 2 hydrogens here, I have 2 hydrogens here. So I have 4 hydrogens in total. Over on this side, I only have 2. So 2 in front to make it into 4. Last thing we need to look at is, do we have the same number of oxygens on both sides? So I have 4 oxygens here, I have 6 here, so I have 10 in total. I have 4, I have 6 now, and I also have 10. So my equation is now balanced. Okay, and so there's that. What we're going to be looking at today is the precipitation reaction. Some of you might know this better as a double displacement or displacement reaction. So synthesis, we already said, is 2 smaller beings creating into a bigger substance. Decomposition is when one substance breaks into 2. Combustion is when we have something burning with oxygen. And then precipitation, that's what we're going to look at today. We're going to try and create some balanced chemical equations to learn about this phenomenon. Okay, so we're going to define what precipitation is, and we're going to look at some solubility rules regarding precipitation. Okay? So how does solubility work? Now think of sodium chloride, an ionic compound. Sodium being a positive ion, so it is a cation, and the chloride is minus, so it is a negative anion, or negative ion, sorry, which is an anion. When water comes down, or when a salt is mixed into water, water is polar, so it has particular parts of it where in the oxygen it's particularly negative, so it has a bit more of a negative charge to it, and then hydrogen has a bit more of a positive charge towards it. So the oxygen being slightly partially negative will want to attract the positive sodium ion away, and so it drags it out. Okay, and that's how it kind of separates. The hydrogen, okay, being slightly positive, will want to drag out the negative chlorine ion. And that's how precipitation works. The different polarities of the water molecule will drag different ions out, making it split apart. And that's why when you mix ionic compounds into water, it will kind of disappear. That's why when you dissolve salt in water, it kind of just disappears, because it's breaking up the fine atoms away from each other. Okay, the next bit we're looking at is just illustrating this. So you see the silver nitrate, it is a solid originally, and it's dissolved into this beaker of water. And what's really happening here is the water is breaking the chemical bonds between the silver and nitrate. So silver nitrate is an example of an ionic compound. And what is occurring here is we're breaking the ionic compound, or the ionic bond. This here is being broken. Okay? Same idea with the silver chloride. So that's breaking the bonds between the two there. Let's say we try and mix the silver nitrate and the sodium chloride together so they come in towards each other. What's happening here now? Well, what we actually see is the water, okay, well, firstly it dissolves the atoms, so it makes it into a liquid solution. So what we mean by an aqueous solution is well illustrated in these two diagrams. If something's solid, you expect that all these atoms are side by side with each other. That's kind of what we showed here. So sodium chloride here is a solid. However, you can see the ions are now dissolved into some kind of solute, or solvent, sorry. And so this is what we call a solution. A solution is where the ions of a salt being dissolved into the water. When you mix the sodium chloride in with the silver nitrate, this is where we see precipitation occur. So what we know is that the silver and the chlorine have a strong attraction towards each other. And that strong attraction between the silver ion and the chloride ion bond them together to make silver chloride. Okay? And so the solid you get after two transparent liquids mix with each other, that's what we call a precipitate, and this forms a solid again. The solid is what we're looking for. Okay? Let's have a look at this again. So a precipitation reaction, we can also call this a double displacement reaction, occurs when cations and anions in an aqueous solution, being the starting point here, combine to form an insoluble ionic solid called a precipitate. And we can illustrate that with this little equation here. Now the precipitate will look something like this. So there needs to be a permanent color change, even if it looks cloudy like this, that's counted as a precipitate. Okay, permanent color changes count as precipitates. It forms a solid, that is also considered precipitate. So these four images here show you a precipitation reaction. Now, if I try to write this out as a general equation, let's say A and C are metals. So A is cadmium, C is potassium, B is sulfate, so the nonmetals, and D is the nonmetal. Okay, so I'll write that out. So we have our metal. So we have our metal here, another metal here. And what happens is the metals swap over partners. So A will swap over its non-metal partner with another non-metal D, and C will swap with its non-metal partner and bond with C. Okay, so we can see this here. In this example here, cadmium will move over to bond with sulfur, and potassium will move over to bond with sulfate. Now it's really critical that you remember the charge numbers of each of these elements when you are changing it up. If you get the charge number wrong, you write the wrong formula and you won't get the right relationship. Okay, so this is how we're going to define a precipitation reaction. Okay, you need to form a solid. So a solid is one of the defining factors of a precipitation reaction. And it occurs between two metal salt solutions. This solid compound, if it's solid and if it's floating in the liquid, then it's insoluble. Okay, so it can't mix with the solution. Anything that just dissolves and becomes transparent, that's what we call a soluble solution. So what we have here, these two reactions here, these are insoluble. Why would we want to use precipitation in our lives? It goes with a couple of things, okay? Mostly it comes with water management. So let's say we have a lot of calcium and magnesium um, metal ions in the water. This causes a thing called hard water, and we don't want that because hard water causes these chemical deposits of these minerals in some very undesired locations. Let me show you with one image here. So you can see these pipes experienced hard watering. So what that means is it's so concentrated with calcium and magnesium that they've essentially crystallized in pipelines and all that. So what we want to do is instead of having all this calcium and magnesium concentrated inside the water, we want to make it form into little solids that we can remove more easily. So that's kind of why we want to use precipitation. In terms of iron and manganese, you might have seen this in some old buildings. This kind of red blood stain on some of the bath arterial. With that's because of the over amounts of iron or manganese in the water. Obviously, it can cause staining and it can promote bacterial growth. So we don't want that. That's why we also need to find ways of precipitating iron and manganese out of our water supply so we don't have this awful staining of your bathroom. The last one is phosphates. Now, phosphates are usually found in fertilizers. And so, if you know a thing or two about geography, usually the fertilizers runs down into rivers and causes provides food for the algae, causing a thing called an algae bloom. A consequence of the algae bloom is eutrophication. Now, eutrophication is where the algae gets so much fuel, it keeps on growing and feeds off the oxygen in the water. So essentially, the algae's continuous growth sucks out all the oxygen inside the water, and then you have fish that end up suffocating in water because it can't actually gather the oxygen in the water, or there might not be any oxygen for it to breathe, and so it suffocates and dies. So that's why we want to get rid of the eutrophication. That's why we need to get rid of phosphates. If we remove phosphates from our rivers, one, we're going to prevent eutrophication, but two, we don't get that ugly looking green algae in water. This is a table that shows you the different solubility rules. Now, we will go through some experiments that explore this in real time, but for now, we just have to look at this and go, these are the rules. Later on, we will show and demonstrate that they are true, but for now, you just have to take my word for it. Where we see the different colors forming between solutions, we know that a precipitate has formed. So we have silver forming with an anion, which is bromide. When silver and bromide come together, it's pale yellow. So the example we looked at earlier on here. And this holds true. One of the things you will know is anything that is a nitrate will not form a precipitate. All group 1 metals, so sodium and potassium, will also not form any precipitates either. So let's have a look here. A complete chemical formula looks something like this. We have the symbol of the chemical, we have the state that the chemical is in. We also have the products that will form. Remember, a precipitation reaction or double displacement just means the metal swaps its nonmetal with another nonmetal. So it just swaps around, comes across like so. Okay? As you can see here, okay, NaNO3 is still aqueous. And we're going to give it a nice little name. We're going to call the two ions that make up this compound spectator ions. Why do I say that? Well, spectator ions are not involved in the overall chemical change or the chemical reaction. We can see that the thing that is undergoing a chemical reaction is the silver and the chlorine. If I looked at sodium and nitrate as little small molecules in a test tube, they will still be in solution. What I mean by that is you'll have silver and you'll have chloride trying to mix it together, and you'll have sodium, or you'll have nitrate, and then you'll have sodium just kind of stuck in solution, not wanting to do anything. They're just watching the reaction between silver and chloride. Okay, so not much is happening for them. Well, if I want to write this out as a complete ionic equation, okay, so a complete ionic equation, you are just writing the ionic formula for each and every element here. So complete ionic formula will look like this. So you'd write the ion of Ag silver, you write the ion for NO3, which is -1. Okay, so you write it all out like this. So you'll need your table. Silver chloride is the only one we don't write the ion for because it's formed a solid. It's not going to be separated if it's a solid. If it's dissolved in water, yeah, but because a solid has formed, we don't need to write an ionic equation, we just write the formula. The next thing we look at is the net ionic equation. So what are the essential bits in this reaction that actually matter? What actually occurred in this reaction? Well, we know that nitrate and sodium did not actually participate in the overall reaction. They were just spectators. They don't add any value to our understanding of the reaction. So I can cancel these out. Okay, I can cancel it out, and also I can cancel it out on the other side as well. And I can rewrite the net ionic equation, which just tells me the essential ions that create this precipitate. So Ag plus, Cl minus, AgCls. Okay? Remember, if it's a precipitate, the starting metal solutions are aqueous, so AQ, and then if you do form a precipitate, it would be a solid, so S. Let's look at some example questions. So let's go through these one step at a time. So question 1 says, define the following terms. What is a precipitate? Well, a precipitate is an insoluble ionic compound. Ionic compound, remember, is just made up of a metal and a non-metal. So I might just write that down. So it's just made up of a metal plus a non-metal. That's what a ionic compound is. And so that is what we see, okay? All right, so the next thing we're going to look at, just move my chair. Okay, so the next thing we want to look at is what is a spectator ion. Now, a spectator ion is any ions that don't take part in a chemical reaction, okay? Question 2, identify your knowledge using this quick quiz. Identify the term for an insoluble substance produced by a reaction in solution. Precipitate. Ions that take no part in a precipitation reaction are called spectator ions. Cloudiness indicates the formation of a precipitate. Okay? So the main thing you need to know is if a solution is insoluble, okay, between a metal and a non-metal, then you would probably form a precipitate. Okay, let's try and make some chemical equations for the following reactions and identify our spectator ions. Okay, so I have iron 3, nitrate, and sodium sulfide. So I formed this reaction here. We'll just go through quickly why it's written like so. So I know that iron is plus 3, nitrate is 1 minus, so it's 1 minus here, that's plus 3 over here. So remember, if they're not the same, you swap the numbers over. That's why it's FeNO3 bracket 3, okay? Sodium is plus 1, sulfur is 2 minus. That's why the 2 comes down here. That's why there's 1 for sulfur here. We know that we made a precipitate of iron 3 sulfide, so iron 3 plus 3, sulfide 2 minus. That's where they come from, the 3 from the iron, the 2 from the sulfur. And then obviously what we know is whatever's not bonded together, so sodium and nitrate, they come together to make sodium nitrate here. Okay? So the spectator ions are sodium and nitrate because they're the ones that are still in solution because it's aqueous. Question 4, write a full equation for the reaction between aluminium nitrate and sodium sulfide in which the precipitate is aluminium sulfide. So I can rewrite that again. Aluminium being plus 3, nitrate being 1 minus, so that's why you see the two differences in numbers. Sodium sulfide we already talked about. Aluminium sulfide, sulfur is 2 minus, aluminium is plus 3, so they swap over if you get rid of the charges. And so sodium nitrate again. So again, we have sodium nitrate as our spectator ions. The next one will require you to look at a solubility table. So before you go through this, I do recommend you have a try of reading through this one first. Silver carbonate, zinc nitrate, copper 2 carbonate, and silver chloride. Which one will be insoluble in water? And if it's insoluble, it'll probably form a precipitate. So silver carbonate is insoluble and it forms a yellow precipitate. It looks something like this. Zinc nitrate, anything that's a nitrate is soluble, so it's just a transparent solution. So it will look completely transparent or some kind of transparent liquid. Copper 2 carbonate is insoluble and you get a green precipitate forming like so. Doesn't look great, but that's what it is. And then we have silver chloride. If you remember, we said silver chloride forms a yellow precipitate, and so there we have that, or white precipitate, sorry. And so there you have our images over here. Question 6, for each of the following precipitation reactions, write a full equation and a net ionic equation. So again, look at your solubility table if you want to do this right. Look at your solubility table. That'll give you a much better hint as to which one forms a precipitate. Now, some of you might be thinking, what if you have two precipitates occurring in one reaction? Generally speaking, you won't get that occurring because the original solutions need to be soluble in each other. So copper is soluble in sulfate and sodium is soluble with carbonate. The reason being is if it's both already in precipitation, so they're both already solid, there wouldn't be any point or reason you'd be mixing them. And then in 7, we're asked to identify the spectator ions above. So let's just firstly write these out. So these are the full equations for my precipitation reactions. If you ignore the fact that I had another copper over there, now this is the perfect equation. So copper sulfate, sodium carbonate, and so on and so on. Okay, now from my data, I know that copper and carbonate forms a precipitate. Okay, so the ions that I'm going to be looking at is the carbonate ion and the copper ion. So that will be part of my net ionic equation here. The other two will be the spectators. So sodium and sulfate will be the spectator ions for this reaction. B, we have ammonia sulfate, barium chloride, ammonia chloride, and barium sulfate. Okay, so already written out for you again. Barium sulfate is going to be the precipitate. Hence, I'm going to only look at the barium and the sulfate ions. So that's what I get. And so my spectator ions will be ammonium and chloride. In question 6C, I find that the precipitate that I create is lead sulfide. And so what I have here, let me actually just check. Looks like I made a little mistake here. So instead of just having sulfur by itself, it should be potassium. Should be potassium 2 sulfate or sulfide, sorry. So we get this equation here. So the only thing that's really to our interest is the lead ion and then the sulfur ion, or the sulfide. And so we get lead sulfide here. So our spectator ions is potassium and nitrate. And so that leads us to the actual reaction, which we will do in another lesson. Thank you for joining with me. My name is Mr. Wong, and I hope you have a very good day.